This is Unit 3, and the first topic is graphing polynomials. So the first thing we're going to talk about is seeing a polynomial in standard form, which is the terms are in order based on the exponents, and then the constant will be last. So the highest exponent will be first, and then the lowest exponent will be last, and then the constant will be after that, versus factored form. And in factored form, we can easily see where the x-intercepts are, or the solutions or the zeros roots for this polynomial. So in graphing polynomials, we use the leading coefficient, which identifies the direction that the right side of the graph is going. And then the degree of the polynomial will tell us if both ends agree or not. So with this one, we have a degree of 4, which means both ends of the graph. So when x goes to positive infinity, or when x approaches negative infinity, they will both be doing the same, show the same behavior. And then the negative shows that they will both be going down towards negative infinity for y values. And then if we are in factored form, we can still see that attribute, but we would have to multiply all the x values out. We can see that it's x to the 4th and that it's still negative. Something else we can see in factored form is the multiplicity of each of the zeros. So if we look here, this is technically x minus 0. We just never write it like that because 0 is nothing. So we just write it as squared, which means at x equals 0, it has an even multiplicity because it's squared. And whenever a root has an even multiplicity, that means it will bounce. It bounces graphically. And we will take a look at that in a second. And then if we look, our x minus 4 and x plus 6, they each have a multiplicity of 1, which is an odd multiplicity. So it's going to pass through graphically. Now there are different types of pass-throughs. For a multiplicity of 1, it's just simply going to cross through the x-axis. But if we see a multiplicity of 3, so a multiplicity of 3, it will create a slide. So think of x cubed. It's going to create that slide motion as it passes through that root or that 0. So we have a picture of the graph over here. We can see that with a multiplicity of 2 at 0, it does have that bounce where it's positive on this side and it's also positive on this side. So it doesn't pass through the x-axis. It's going to stay the same sign as far as the y values. And then for x is equal to 4 and x equals negative 6, we see that with the multiplicity of 1, it just passes through. So something that we will be talking about later, but not necessarily right now, but I would like to introduce it, is a sign pattern. We are able to sketch the behavior of these graphs using the signs of the output values. So I have my roots, negative 6, 0, and positive 4. And basically what a sign pattern is going to tell us is are the outputs negative or are they positive? So if we go back to the standard form, we can see that this is negative x raised to the 4th. That negative tells me that the right side of the graph will be going down, but that 4 tells me that the negative side will be doing the same as the positive side. So that negative side, or that negative in front of the x to the 4 tells me that this is negative, but because it's an even degree, both of them will be doing the same thing, going in the same direction, which is negative infinity. Now, if I start from the left, I know this has a multiplicity of 1, so the y values will change signs because it passes through. 0 has an even multiplicity, so the sign will stay the same. And then 4 has a multiplicity of 1, so the sign will change back to negative. So this is a quick way to understand. If you don't have a visual of the graph, you're able to sketch this out, and it can tell you a lot about what's happening at these roots and with the y values. But again, we'll see that later. Okay, and then I also want to talk about the fundamental theorem of algebra. I asked my classes if anyone has heard of this, and they haven't, but I think it's important to understand what's the foundation for algebra, like what are we doing? And you've all been working with this method, but it's just to put a name to a face, basically. So this is any polynomial of degree n has n roots. but there might be complex numbers. There might be complex numbers. Again, you know what the roots are, and you know that the degree of a polynomial will tell you the number of roots that it has. Okay. So example 1, from the function f of x displayed above, which is the graph we see on the right, identify all relative extrema, high or low points in a relation to nearby points, and also find any absolute extrema. And this is the high or low point for the entire graph. So first thing I want to mention is that you're going to see these terms used interchangeably is absolute extrema and global extrema. They both mean the same thing, and that's going to be the absolute highest output and then the absolute lowest output. And then for relative, you're going to see the word local used with this. So make sure you're familiar with both of these types because you're going to hear about them. So we can use the calculator for this. So I'm going to switch to here. All right, I'm going to go ahead and plug in my function. And in the notes for the top of it, it was negative x to the fourth minus 2x cubed plus 24x squared. Now, get out of the habit of just going straight to the graph because most of the time you're not going to be able to see the attributes of the graph that you want to see. So go to your window, and if you look on the notes, the x values are going from -7 to +3. So I'm just going to copy that. And then I want to be able to fit all of my extrema, so I'm going to hit zoom 0, and that's zoom fit. I think I hit the wrong x value. It should be going to 5, yeah, so not 3. There we go. So now with zoom fit, it adjusts your window to fit all of your y values. Okay, so the problem is asking to identify all relative and absolute extrema. So I'm going to read from left to right. If I go from the left side, I have a maximum. So I'm going to do second trace and go down to number 4, and I'm going to travel over to the maximum. So we'll hit enter, and then we'll go to the right side and enter. And this should be a review. You did this last year in Algebra 2. And then guess, I don't want to, and it says that I have a maximum at x equals -4.294 with a value of 260.895. So before switching back to the notes, I'm going to go through all 3 of them. So after this, I'll hit second trace. Next, I want to find that minimum at 0. We already know what this is. It's going to be 0, 0, but I want to show you something in the calculator. All right, so if you look at this, it says x equals 1.279. The e means times 10 to the power of -6. This is a glitch in the TI-84. This is just 0, 0, right? So if you see the calculator do this, don't write all of the coordinates that you see. It's simply 0, 0, okay? And then we'll do the last one, which is another maximum. So second trace, we'll go down to number 4. And I'm going to go over to this one. We'll hit it there. And then we'll also hit it here for the right bound. And we get the other maximum. So before we go back to the notes, I want to talk about this. If we look at the maximum on the left side, that is relative, but it is also the absolute maximum for this function. That maximum is the absolute highest y value of the entire function. So it is a relative maximum, but it is also an absolute maximum. All absolute extrema are relative extrema because they fit the definition of a relative extrema, which is it's the highest point within the neighborhood of points around it. And then at 0, we have a relative minimum. And then the last one we did was a relative max because it's the highest within the neighborhood of points around it, but it's not the absolute highest. And then same with the minimum at 0. It's the lowest point in that neighborhood, but because the function is going to -infinity, that is not the absolute lowest y value. So we'll go back to the notes. All right, so listing these out, there is a specific way to analyze these. We will say a relative, we'll go ahead and write it out. So we have a relative maximum, you need to state what type of extrema are you looking at and the value of it. So that left one was a relative maximum of 82.792, and you want to use at least 3 decimal places at x equals 2.974. So you're stating what type of extrema it is, the value of that extrema, and where it's located. Now, the one on the left side, that was a relative maximum, and it was also an absolute maximum. So we also have an absolute maximum of 82.792 at x equals 2.974. And to determine which one you write, it depends on what the question is asking. This says identify all relative and absolute, so I felt compelled to write both. If it just said relative, then just write relative. If it said absolute, you would only have one answer, which is that absolute maximum of 82.792 at x equals 2.974, because there is no absolute minimum. We also had a relative minimum of 0 at x equal, oops, I should not say and, at x equals 0. And lastly, we had that maximum, relative maximum, of 260 0.896 at x equals negative 4.294. And I just noticed something. I switched my maximums. So this one, that second one, I mixed up my left and my right maximum. And I noticed that because of the y value. So my absolute was this one, 260. Obviously, because I can see that it's greater than the 82, okay? So we'll say the absolute maximum of 260.896 at x equals negative 4.294. So my absolute maximum is here, which is the 260, and then my relative maximum is here, which is the 82. Okay, so I got them switched the first time. Sorry about that. All right, part B says identify the domain for the increasing intervals and also the decreasing intervals. So your relative extrema are going to help create the intervals for this, all right? And this should be your x values. The domain will be your x values. So f of x is increasing, and you should write these as a statement as well in interval notation or inequality notation on. Now, if we go back up to the graph, we see that we have a maximum at x equals negative 4.294. So when a function reaches a maximum, it increases into the maximum and decreases out of it. So that function is that function is increasing from negative infinity all the way up to that maximum that is at negative 4.294. So that's the first interval. It's increasing into the maximum. And then if we look again, so the interval we just did was this one. It's increasing. And if we look again, we have a second maximum, which means the function has to increase into that maximum again, which is going to be from 0, from the minimum, to the other relative extrema, which is at 2.974. So we're going to union. It'll be from 0 to 2.974. So the function is always increasing into a maximum. So find your relative maximum and then see where it's increasing from. It'll either be from negative infinity or from a minimum. So now we'll cover decreasing. F of x is decreasing. So f of x will decrease out of a maximum, okay? So we know that we have a maximum at x equals negative 4.294, so it's going to decrease out of that, or just pick up from where the increasing left off. And it's going to decrease up into the minimum, which is at 0. Or just, it's going to go to where the other increasing interval is starting. Union, and then it's going to decrease out of that maximum again to positive infinity. So from 2.974 to positive infinity. And again, you should write those as statements. Don't just put an interval. You want to explain what does the interval represent. And then the last part is, where does f of x equals 0? We already talked about the roots for this. It's going to be at x equals -6, x equals 0, and then x equals 4. And then where is f of x greater than 0? This is talking about the y values, and it's the y values that are above the x-axis. Not equal to, but above. So if we look at this graph, we'll use the x-intercepts. It is going to be positive from -6 to 0, and also from 0 to 4, okay? So sometimes the intuition is to write down -6 to +4, but that poses a problem. This doesn't say when f of x is greater than or equal to. It strictly says greater than, which means we cannot include 0, -6, or 4. None of them can be included in our interval, so this won't work, okay? We have to write an interval from -6 to 0, union 0 to 4. We have to make sure that we are excluding our x-intercepts, which are -6, 0, and 4. And then same thing for when it's negative, when the outputs are negative. That's going to be down here. So for this tail end and that tail end. So from -infinity to -6, the y values are negative, and then from 4 to infinity, the y values are also negative. So -infinity to -6, union 4 to infinity. All right, and that's the start of Unit 3. Hope this helps.